Like and subscribe. Generators, which are connected to the network through power electronic converters, e.g. wind farms, photovoltaic plants, etc. Wind turbine generator type 1. Type 1 is a squirrel cage induction generator connected directly to the step-up transformer. The turbine speed is fixed to the electrical grid frequency. It generates real power when the turbine shaft rotates faster than the electrical grid frequency, creating a negative slip. Wind turbine generator type 2. Type 2 is a wound rotor induction generator with a variable resistor in the rotor circuit. This can be accomplished with a set of resistors and power electronics external to the rotor, with currents flowing between the resistors and rotor via slip rings. The variable resistors are connected into the rotor circuit and can control the rotor currents in order to keep constant power even during variable wind speed conditions. Wind turbine generator type 3. Type 3 is a variable speed asynchronous wound rotor generator which has a three-phase AC field applied to the rotor from an AC to DC to AC converter, the power source for which is the generated voltage. AC excitation to the rotor circuit. The additional rotor excitation is supplied via slip rings by a current-regulated voltage source converter, which drives the rotor currents. This rotor side converter is connected back-to-back with a grid side converter, which exchanges power directly with the grid. Wind turbine generator type 4. Type 4 is an AC generator in which the stator windings are connected to the power system through an AC to DC to AC converter. This turbine type offers a great deal of flexibility in design and operation, as the output of the rotating machine is sent to the grid through a full-scale back-to-back frequency converter. The turbine is allowed to rotate at its optimal aerodynamic speed. Photovoltaic generator refers to the total of all PV strings of a PV power supply system, which are electrically interconnected. A PV string is a circuit in which PV panels are connected in series, generating power in DC voltage and current. An inverter is needed in order to connect the PV to the grid. Doubly fed induction generator. In doubly fed induction generators, the stator is directly connected to the grid and the rotor is connected to the grid by back-to-back converter. This connection allows the generator to operate within a wide range of axis speed, and therefore presents the advantage of the possibility of working at variable speed, giving a good damping against wind speed variations. This system allows using small power converters, as just a little part of power is transferred between rotor and grid. During severe short circuits, the voltage in the stator decrease, and due to magnetic coupling between stator and rotor, high voltages and currents could be induced in the rotor and consequently on the converter. Crowbar. DC chopper, a barking resistor is installed in parallel to the DC converter capacitor. In case of severe grid fault, the DC chopper will limit overvoltages in DC link, and these resistances will dissipate the energy that cannot be delivered to the grid due to the short circuit. Crowbar, resistors driven by thyristors are installed on rotor side. During severe grid voltage dips, high overcurrent will be induced in the rotor. In order to prevent this overcurrents flowing through converter, crowbar thyristors are triggered, allowing most of short-circuit overcurrent flow through crowbar instead of converter. Gear. Very severe faults where the crowbar is applied and not removed. In this case, the DFIG provides the fault current performance of an induction machine. Faults of insufficient severity to cause crowbar operation. In this case, the DFIG provide the fault current controlled, and the performance is very similar to a Type 4 wind turbine. Protection scheme for back-to-back converter control strategies. Converter protection, crowbar and/or DC chopper. Full converter wind turbine generators are synchronous machines directly connected to the grid by a back-to-back converter. They need a bigger converter than Type 3 wind turbines, as the full power flows through converter. This technology presents the following characteristics: the flow is independent from the network. High power converter. Torque control independent from the network. Active and reactive power are fully controlled by the grid side converter of the back-to-back. Converter controllers are really flexible, and they are programmed in order to comply with the requirements of the grid codes. Under fault conditions, the behavior of the Type 4 wind turbine depends on the converter controls. Photovoltaic panels generate power in DC, and therefore, an inverter is needed to connect a photovoltaic power plant to the grid. In the same way as Type 4 wind turbines, their performance under short circuit is completely defined by inverter controller, so the same explanations as for the Type 4 wind turbines can be assumed in terms of short circuit contribution. 3 protection functions. Differential protection. This function is commonly used as main protection function to detect short circuits in line due to its high reliability. A communication channel is needed in order to exchange current measurements between both ends. Under normal operation without fault conditions or external fault condition, phasor current measurements in both ends must be equal in magnitude and have 180 degrees angle difference, so there is no differential current measured in the protection devices of the both ends. Line differential characteristics follow two slopes. Slope 1, it is applied for low restrained currents. In this case, errors in magnitude and phase due to the magnetizing current of current transformers are small and slope to restraint used to be small. Slope 2, it is applied for high restrained currents. Saturation of current transformers in case of external faults could generate high differential currents in protection devices of both ends. In order to avoid unwanted trips 87L trips in case of external faults, a second higher slope is implemented to ensure stability. This function is commonly employed as line protection in protection schemes, and when no communication system is available, distance protection function is used as main protection function. The principle of this protection function is to measure the positive sequence impedance from protection measuring point to the fault. As impedance is proportional to the line length, it can be calculated as the distance to the fault from impedance seen by the protection device. Impedance principle measurement of distance protection. Load flow conditions before the fault and fault resistance are the main factors that introduce errors in the impedance measurement. Distance protection function implements complex algorithms in order to detect fault condition, identify faulted phase, and calculate impedance, so the way these algorithms are developed in the protection device will have strong impact on the protection behavior. Characteristic and quadrilateral characteristic. Mo characteristic. This characteristic is traditionally employed to detect phase-to-phase and three-phase faults. Quadrilateral characteristic. Due to the better resistive coverage, this characteristic is used for single line to ground faults and phase to ground faults. Nowadays, its use is increasing for phase-to-phase faults and three-phase faults in order to get more resistive coverage. Directional earth fault protection. Directional earth overcurrent provides an additional coverage to phase ground faults that may not be detected by the main protection functions. When a fault to ground has a high resistance, it may be out of resistive coverage of the distance protection. In order to detect high resistive faults, directional earth overcurrent relays have been commonly used in protection schemes. The operating magnitude of 67 N is the earth current. As this 3I0 current can be originated by faults from any phase to ground, in order to obtain directional performance a reference magnitude is needed. This magnitude is the polarizing quantity. Zero sequence voltage is commonly used as polarizing quantity, although it is possible to use other magnitudes if the zero sequence voltage is not able to polarize the relay without producing deficiencies, or there are magnetic couplings between circuits, and then -3V2 amplitude can be used instead. It is possible to use 3I2 as polarizing quantity since it may be a more trustable magnitude. For PEIG short-circuit current contribution. PEIG has a strong dependence of power electronic control as they are connected to the grid through power electronics converters. This represents a strong difference against classical synchronous generators, where power electronic converters are mainly used for excitation systems, but never interfaces with the grid. Another important factor that affects the short-circuit current contribution is the speed of the converters, as well as their dynamics. It can be assumed generally for almost every PEIG that the speed of the control is a critical parameter to take in account in terms of short-circuit contribution, and therefore it has a strong impact in protection behavior. Converter protections. Crowbar is connected to protect the rotor and the converter from overcurrents produced when severe voltage dips occur. In case of severe voltage dip, the crowbar will act and bypass the current that could damage the rotor and the converter. When crowbar is connected, the behavior of the DFIG is similar to induction generator. When the crowbar is not connected, the rotor will continue to be powered during fault and the rotor voltage is adjusted by excitation system. Converter control. The control strategies will have strong impact on the currents injected during short circuit and therefore in the behavior of protection algorithms. Several strategies are taken not just to fulfill fault ride-through requirements but also to provide support to the grid when voltage dips appear. Under unbalanced grid condition, DFIG control is affected by double-frequency oscillating magnitudes. One of the strategies that can be applied to the negative sequence controllers of the converter is to minimize these oscillations in the controls through the decoupling of positive and negative sequence components. Figure 8 shows an example of short-circuit contribution from DFIG under 3pH fault with voltage dip of 20% pu on step-up transformer MV. The grid codes specify the requirements to PEIG in case of voltage dips, establishing the time that a PEIG has to be connected to the grid and the reactive power supply according to the severity of the voltage dip in order to improve voltage stability. Nowadays, most of the European grid codes do not require negative sequence injection in case of unbalanced faults, and they usually implement only positive sequence injection for any type of fault. Then short-circuit current contribution from full converter will be balanced in that case. The control strategy implemented in the converter, both in the positive and in the negative sequence reference frames, will define the short-circuit current contribution for full converter generators. Figure 9. Full converter sequence networks for 1 phg fault with injection of negative sequence. Usually, the injection of negative sequence current is performed or it is potentially requested proportionally to the negative sequence voltage in order to differentiate between balanced and unbalanced grid fault conditions. As it was mentioned, the speed of the control is a factor that affects directly to the short-circuit contribution. Sometimes the speed of the control depends on the stiffness of the grid connection points, or in other words, the short-circuit ratio. When PEIG are connected to weak grids, vendors tend to make the control slow or reduce the control bandwidth in order to avoid control interactions. This would mean slow injection of reactive currents during the faults. Functions of transmission lines. For all full converter interfaced PEBG and MMC HVDC stations, there is default implementation of negative sequence current from vendors. The vendors implement negative sequence suppression control and control the negative sequence current flow to zero during unbalanced faults in order to protect the IGBTs for high uncontrolled unbalanced currents. It is the injection of the negative sequence current proportionally to the negative sequence voltage at the PCC that would enable negative sequence current flow. On the other hand, negative sequence current suppression control results in zero negative sequence current. Nowadays, the algorithms implemented in protection relays devices are based on short-circuit current contribution from synchronous generator, and the question that arises is if these algorithms are still valid for networks with high penetration or PEIG. Impedance measurement. In cases where crowbar is activated and not removed during the voltage dip, short-circuit contribution is similar to induction generator and impedance measurement will not be affected. When voltage dip is not so severe, crowbar is not activated and short-circuit current contribution is driven by the converter. During the transient state in which converter control is acting to supply the limit current, impedance measurement can be affected due to the current waveforms of these transient state. After this transient state, DFIG generator is supplying currents according to the control implemented in the converter control, and impedance measurement will be probably accurate. Multiple switching of the crowbar has a great impact in short-circuit contribution, obtaining current waveforms not predictable and not purely sine. Under these conditions, calculating the current and voltage phasors will be difficult for protection devices due to current and voltage waveforms. Therefore, the conventional impedance measurement can be strongly affected during multiple crowbar switching. Faulty phase selection. As explained in previous chapters, the crowbar action is affecting the short-circuit current contribution from DFIG generators. Algorithms based on superimposed quantities can be affected due to the current waveforms in case of multiple switching of the crowbar. Then, errors in faulty phase selection could be expected in case of implement superimposed quantities algorithms. As DFIG generators under unbalanced faults injects negative sequence currents, algorithms based on are expected to present good behavior even in case of multiple switching of the crowbar. Current are expected to be affected under unbalanced faults. Injection of negative sequence strategy. In this case, performance of algorithms based on phasor angle difference between negative sequence current and zero sequence current are expected to work properly under unbalanced faults. As this function is two-ended protection or single object-oriented protection, short-circuit currents under fault condition could be enough to pick up the function, regardless of the kind of generation connected to the end buses. It could be guessed that as long as you have a strong end with synchronous generation, pickup level will be asserted for the weak end too. Directional earth over current. Pickup current level sufficient to pick up the directional earth fault and no issues are expected to pick up 67 N. In cases where polarization magnitude is negative sequence voltage and operation quantity is negative sequence current, as DFIG generator injects negative sequence current in case of unbalanced faults, no issues are expected to pick up 67 N. Sufficient to pick up the directional earth fault, and no issues are expected to pick up 67 N. Negative sequence current, as the negative sequence current injection depends on the control current will not provide operation magnitude and issues with pickup level of 67 N are expected. Directionality. Negative sequence current, as DFIG generator injects negative sequence current, directionality issues are not expected. Negative sequence current, as negative sequence current injection depends on the control current will not provide operation magnitude for the directionality of directional earth fault, and it could lead to wrong polarization of 67 N.